Hey guys, Mrs. Harpin here, and we're back with another pre-calculus video today. This time we're looking at 1.2, trigonometric ratios, or trig ratios for short. Our biblical application is this. We know that God made angles as a part of our world. They represent a place where things come together as well as how things are oriented to each other. Unlike lines, which are infinite, angles show God's use of a finite system of measurement. We know that we can build things and create things precisely. We can duplicate things that other people have created because of this orderly and finite system of measurement. Our objective today is this. The student, you, will be able to state and apply the Pythagorean theorem and define the 6 trig ratios by the end of today. Now, when we talk about trig ratios, we are talking about the relationships between the sides in right angles and right triangles. And these are true for all triangles that have a right angle. Thank you for God for creating these patterns and these ratios that hold true no matter what. When we talk about the legs of a triangle, right triangle, we're talking about the two sides that form the 90-degree angle. In this case, we're talking about leg lowercase a and lowercase b. Our angles themselves are labeled with capital letters. The hypotenuse is that third side, in this case, labeled with lowercase letter c. Now, the Pythagorean theorem, which was quote-unquote discovered by Pythagoras, although historians argue about whether it was actually Pythagoras who discovered this or whether it had been used for years and years and years before him, and he's just the first person who published it. Regardless, he's the one who kind of made this theorem famous. And what the Pythagorean theorem says is that in right triangle ABC, the sum of the squares of the lengths of the legs is equal to the square of the length of the hypotenuse, or a squared plus b squared equals c squared, which is what you are probably most familiar with. Now, this theorem has been proven in over 200 different published ways, from students like you yourselves who've proven it one way, up to presidents of the United States who come up with their own proofs. Over and over and over again, we see this special relationship between the sides of a right triangle and that hypotenuse. A squared plus b squared equals c squared. Now, the 6 trig ratios are related to the sides of a triangle, the sides of a right triangle. And this first trig ratio is the sine. The sine of angle A, which is just sine A. And the sine ratio is the ratio between the leg opposite of the angle, in this case, angle A, and the hypotenuse. Like we do in many other subjects, we come up with these handy little acronyms and other things to help us remember things. And so to help you remember sine, we have sine is opposite over hypotenuse. In this case, if we're wanting to find the sine of angle A, we go to the side opposite angle A and the hypotenuse, which is side C. So sine is going to be SOH, S-O-H, so. Opposite over hypotenuse, A over C. The cosine of angle A, so this cosine relationship is the leg adjacent to the angle that we're talking about, in this case angle A, over the hypotenuse. Adjacent over hypotenuse, which in this case, the side adjacent or next to the angle A, the leg adjacent to angle A, I should say, is side B. And the hypotenuse stays the same at side C. So we had sine was S-O-H, so, and cosine is C-A-H, ka, so, ka. And that brings us to the third trig ratio, the third of the 3 most important trig ratios, and that is tangent. If we were wanting to find the tangent of an angle, we take the leg opposite over the leg adjacent. Opposite over adjacent, which in this case, the leg opposite of angle A is side A, and the leg adjacent to angle A is side B. So tangent is opposite over adjacent. Just to remind yourselves here, refresh, we had sine was opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent, the tangent ratio is opposite over adjacent. So, ka, and toa. So, ka, toa. You'll hear that said like it's an ancient word, but it's really just to help you remember those three trig ratios. The other three trig ratios, called reciprocal ratios, are reciprocals, hopefully you remember what that means, of the three basic ratios. The cosecant of A, written like this, CSCA, is just 1 over sine. So it's the opposite or reciprocal of sine. Where sine was opposite over hypotenuse, cosecant is, flip that over, hypotenuse over opposite. The secant of A, written SECA, is 1 over cosine. If cosine was adjacent over hypotenuse, then secant is, that's right, hypotenuse over adjacent, written this way. And cotangent of A is the reciprocal of tangent, written COTA. It's 1 over tangent. So if tangent was opposite over adjacent, then cotangent is adjacent over opposite. That is correct. So those are the 6 main trig identities, or the 6 trig identities that you need to know. So let's do some practice finding all 6 trig identities for angle G in this right triangle EFG. We know that E, side E, lowercase e, it's the opposite of angle E here, is 6, and side F, the opposite of angle F, side F is our hypotenuse, F is 8. We're going to use the Pythagorean theorem, first of all, to find G. We know that leg squared plus leg squared equals hypotenuse squared. In this case, we've just replaced the letters in the Pythagorean theorem with the letters that we're using to represent this triangle. So leg squared, G squared, plus E squared equals hypotenuse, which is F squared. We know that G is 2 times the square root of 7, and E is 6. Let me go back here. And E is 6, so to solve that, we would have to have back up just a moment. I forgot what I was trying to find. We're told that E is 6 and that F is 8. Using our Pythagorean theorem, we're trying to solve for G. We know that 6 squared is 36 and 8 squared is 64. And when we conduct the algebra on that and simplify that, then we find that G is 2 square root of 7. Sorry for any confusion there. So let's move on to our trig identities. Starting with sine, we know that sine is opposite over hypotenuse. Well, the side opposite of G is, that's right, lowercase g, 2 square root of 7. And the side adjacent, or the leg adjacent to G, is 6. Remember, we're looking at legs when we talk about opposite and adjacent. We are not looking at the hypotenuse. 2 square root of 7 over 8 simplifies to root 7 over 4. Let's go ahead and find our cosine. Our cosine is adjacent over hypotenuse. See if you can write the values that you need for adjacent over hypotenuse. Our adjacent side is 6, our hypotenuse is 8, and that simplifies down to 3/4. Great job. All right, our tangent is opposite over adjacent. See if you can find the values there. We know our opposite side is 2 root 7 and our adjacent side is 6. That's going to simplify down to root 7 over 3. So we've just found our first 3 trig values, sine, cosine, and tangent. Cosecant is just the reciprocal, 1 over sine. We know that sine was root 7 over 4, so the reciprocal, we flip those around. Our secant is 1 over cosine. And our cotangent is 1 over tangent. If you need to back up and watch what those original cosine, sine, and tangent values were to make sure we're actually doing the reciprocals, go right ahead. Now, you may notice that for sine and for cotangent, we have an extra step right here. That's because we don't want to leave a square root symbol in the denominator of our fraction. We need to do what's called rationalizing that fraction. Hopefully you learned that in Algebra 1 or Algebra 2. But basically, we're just going to multiply the top and the bottom by root 7. Square root of 7 times square root of 7 gives us just 7. And square root of 7 times 3 is 3 root 7. Now we've gotten that irrational number out of the denominator and moved it up top. You'll notice that we did that with sine as well, and I skipped right over that. Now we do have some special triangles in the geometry and trig world, and hopefully this is not new information, but our first special triangle is the 45-45 triangle. This is where the 90-degree angle is right there, and our two other angles are 45-degree angles. In a 45-45 triangle, our two legs are congruent. So let's see if we can find Q. We know two legs. We have to find the hypotenuse. What are we going to use? Maybe the Pythagorean theorem? Hopefully that's what you said. According to the Pythagorean theorem, the 2 legs squared equals a hypotenuse squared. So 1 squared plus 1 squared equals Q squared. 1 squared plus 1 squared is 2. 2 equals Q squared. And in order to get Q by itself, we've got to take the square root of both sides. Just a little bit of algebra here. That gives us Q equals square root of 2. Erase my ink so you can see it there. The sine of a 45-degree angle then is 1 square root of 2. 1 over square root of 2, but we've got to rationalize that denominator, and when we do, we get root 2 over 2. We also have some other special triangles, like the 30, 60, 90 triangle. Let's see if you can find the tangent of a 30-degree angle. Hopefully you remember tangent. So TOA, T-O-A, tangent is opposite over adjacent. That's right. First, we need to find side B, and we're going to do that with the Pythagorean theorem. 1 squared plus b squared equals 2 squared. We find out that side B is root 3. There it is on that triangle. Using our trig ratios, we find out that tan of 30 is 1 over root 3. Let's rationalize that denominator, and that leads us to square root of 3 over 3 as our tangent of that triangle. We know that sine is opposite over hypotenuse. Sine of theta, any angle, is opposite over hypotenuse. In this case, on the Cartesian plane, our opposite is going to be represented by y, and our hypotenuse is going to be represented by r. If this were a circle, a very badly drawn circle, this r is equivalent to our radius. So we're going back to those degrees and radians in that unit circle that we learned about in lesson 1. Cosine, we said cosine is adjacent over hypotenuse. In this case, it's going to be our x-intercept, our x value over r, the radius, and our tangent, opposite over adjacent. That's going to be our y over our x. From there, then we can derive our